In section 5.1, we look at systems of linear equations and inequalities in two variables. This should be a review topic for most of you. A system of linear equations in two variables is basically two equations of lines, like you see here. So we have ax plus by equals e, cx plus dy equals f. These two equations are written in standard form. When solving a system of linear equations in two variables, basically all you're doing is looking for the point where two lines meet. So if you think about graphing two lines, there are three different things that can happen. The most common and most interesting thing that can happen is the two lines meet in one point, which means there is one solution. And that's what happens here. Or the lines could be parallel, like you see here. And if they're parallel, that means they do not intersect, which means that there is no solution. And the last thing that can happen is when you graph the two lines, one line might be directly on top of the other line. So in other words, the two lines are actually the same line. And in this case, there are infinitely many solutions. Let's talk about some methods for solving systems of linear equations. In our first example, they ask us to use the elimination method to solve the system of equations. And I will be going over the elimination method, but I want to let you know there is also a method called substitution, which they don't really outline too much in the book. But let's go ahead and use elimination. So the idea is, when given a system of linear equations, first of all, you want them to be in standard form. The reason for this is because you can see the x variables line up, the y variables line up, the equal signs line up, and also the constants line up. Now what I would like to do is add these two equations together. But you can see if I add these two equations together right now, what I get is just another equation of a line. And this is not useful. So instead, what I want to do is take one of the two equations, or both if necessary, and multiply it by a constant so that when I add the two equations together, something cancels. So for example, if I want to cancel the x's here, when I add these together, I need these to equal 0. And the way to get that is to multiply this x term by -3. So basically, we have to take the system and multiply the first equation by -3 on both sides. When I do that, if I distribute the -3 here, we get -3x minus 3y is equal to -90, and the second equation will remain unchanged. But now you can see if I add these two equations together, the x terms cancel out. -3y plus 8y is 5y, and -90 plus 180 is 90. And now I can simply divide both sides by 5 to get y equals 18. Now, this is only half of the solution. Remember, if you get a solution to a system of linear equations, it's supposed to be a point where two lines meet. So if I take y equals 18 and I plug it back into the original equation, we get x plus 18 is equal to 30. And by subtracting 18 from both sides, we find out that x is equal to 12. So the solution is 12, 18. X equals 12, y equals 18. So these two lines meet in a single point, and we were able to find it. And this method is called the method of elimination. Now I want to talk about a method called substitution. To use the substitution method, we're going to take the first equation, and we're going to solve it for y or solve it for x. It doesn't matter which variable you solve for. I'm going to solve for y. So I can do this by subtracting x from both sides. and this gives us y is equal to 30 minus x. Now from here, I take the second equation, and I'm going to take the expression 30 minus x and substitute it in for y in the second equation, because y is equal to that. If I do that, I get 3x plus 8 times y, which is replaced by 30 minus x, is equal to 180. And from here, I just solve this equation. So we have 3x plus 8 times 30 is 240. 8 times negative x is negative 8x. Then we can combine like terms. 3x take away 8x is negative 5x. And from here, subtracting 240 gives us negative 5x is equal to negative 60. And finally, dividing by negative 5, we end up with x is equal to 12. And now that I know x equals 12, I can substitute that back into the original substitution to get y equals 30 minus 12, which is 18. And this gives us the solution 12, 18. And you'll notice that that's the same solution we got before. One final note here is that if you choose to use elimination, you can eliminate either variable. So in the first attempt, I eliminated the x's by multiplying the first equation by negative 3. But we also could have eliminated the y's. To do that, we would have to multiply the first equation by negative 8 to cancel the y terms. Let's take a look at that. So if I multiply the first equation by negative 8, what we end up with is negative 8x minus 8y is equal to negative 240. The second equation is unchanged. And now when we add these together, the y's cancel out, and we end up with negative 5x equals negative 60, which looks really familiar. That gives us x equals 12, and then substituting x equals 12 into the original equation will once again give us y equals 18. So when using the method of elimination, you can eliminate either variable. So what I recommend is just to eliminate whichever variable is easiest. In the next example, we are going to solve several systems of equations, and I'm going to use the method of elimination like they ask us to. So let's go ahead and go through these. Let's take a look at the first one. In the first equation, if I choose to eliminate the x's, notice that I would have to multiply both equations by something, because the least common multiple of 3 and 5 is 15. So I would need to multiply this by 5 and this by 3. And what I mean is I would have to multiply the whole first equation by 5 and the whole second equation by 3. However, if I choose to eliminate the y's, notice that the least common multiple of 2 and 4 is 4. So if I choose to eliminate the y variable, I only need to multiply the first equation by negative 2. If I multiply both sides here by negative 2, and I distribute, I end up with 6x minus 4y equals 10, and the second equation is the same. And now you can see that we have negative 4y and positive 4y. Now one other note that I want to make is I had to multiply by negative 2 because the only way these cancel is if they have opposite coefficients, right? So we need one negative and one positive. From here, if we add these together, we get 11x is equal to 22. Dividing by 11 gives us x is equal to 2. And now I can take x equals 2 and plug it into either one of these equations. I'm going to choose to plug it into the second equation because there's no negatives there, so it seems like it might be a little bit easier. So if x equals 2, we get 5 times 2 plus 4y is equal to 12. This is 10 plus 4y is equal to 12. Subtracting 10 from both sides, we get 4y equals 2. which means y equals 2 divided by 4, which is 1/2. So the solution here is x equals 2, y equals 1/2. For the second system, I take the same approach. Suppose I want to cancel the x's here. I would need both of these to be a 4, right? One needs to be positive and one needs to be negative. We already have a negative and a positive, so all I need to do is multiply this first equation by 2. If I do that, I get negative 4x plus 2y is equal to 8, and the second equation is positive 4x minus 2y is equal to negative 8. And when you add these two equations together, something really interesting happens. Everything cancels. So you end up getting 0 equals 0. Now, what that means is you don't have one solution, right? You either have no solution or you have infinitely many solutions. But since 0 equals 0 is a true statement, this means that the two lines they gave us in the beginning, these two lines here, they're actually the same line. And what that means is there are infinitely many solutions. So this means that these two lines are the same line and they intersect in infinitely many different points. But what points do they intersect in? This only tells us how many solutions we have. It doesn't tell us what the solutions are. So to get those solutions, we have a couple of different ways of writing the answer. One way to do it is to say that the solution is the set of all points x and y, such that what has to be true about x and y is it has to satisfy these equations. But again, these equations are the same, so we can pick either one of these. So I'll just pick the first equation. Negative 2x plus y is equal to 4. So we're basically saying here the solution is all points on the line, right? All points x and y that are on this line. There is another way to represent the solutions. Another way to do it is to simply write the equation. So we have negative 2x plus y is equal to 4. And if you solve for y by adding 2x to both sides, you get y equals 2x plus 4. So the points that are on this line are all points where y is equal to 2x plus 4. So if the x-coordinate is x, the y-coordinate is 2x plus 4. This describes all the points on the line. So for example, if I let x equal 1, that would give us the point 1, 6. So 1, 6 is one of the solutions. If I let x equal negative 2, then negative 2, positive 2 would be a solution. If I let x equal 0, then 0, 4 would be a solution. So all I'm doing here is plugging in any value for x and then getting the corresponding value for y, and these are all solutions to this system. So we could keep doing this indefinitely. Now, a lot of times when you're doing homework, I think this is especially true for online homework systems, they will simply ask you to describe the type of solutions you have, and so you would just say there are infinitely many solutions. But really the solution should be written as the set of points that satisfy it. So you should either write your solution like this, or you can write your solution like this. So there's a couple of different ways to express your answer here. For the third system, we're going to eliminate the x variable. To do this, we need this negative 2 to be a positive 6. So I'm going to multiply both sides of the equation by negative 3. When we do that, the first equation becomes 6x minus 3y equals negative 12. And the second equation is negative 6x plus 3y is equal to 10. Now you can see when you add these together, the x variable cancels, the y variable cancels, That leaves you with 0 on the left side, but on the right side you have -2. Okay, so this is another special situation, but this is a false statement. And when you get a false statement, what that means is these two lines do not intersect. So what we have here are parallel lines. And that means that there is no solution. Now let's take a look at an application. In 2015, the U.S. travel and tourism industry generated $1.5 trillion through both foreign and domestic tourists. Domestic tourists generated 4 times as much revenue as foreign tourists. How much revenue was generated by each type of tourist? So we have the domestic tourist. We're going to say that they generated X dollars of revenue. And we have the foreign tourist, and we will say that they generated Y dollars of revenue. And we know that X plus Y is equal to $1.5 trillion. And for this, we'll just express this in trillions. And so we can take off the dollar sign and take off the trillion here. But we also know that domestic tourists generated 4 times as much revenue as foreign tourists. So the amount of money that the domestic tourists brought in is equal to 4 times the amount of money that the foreign tourists brought in. So X is equal to 4 times Y. So what we have here is a system of equations. X plus Y equals 1.5. And X is equal to 4Y. Now you could use elimination here. To use elimination, you would need to write both of these equations in standard form. So I would have to subtract 4Y from both sides and write the equation like this. But I'm not going to choose to do the problem this way. It's actually much easier just to use substitution, because you'll notice that X is equal to 4Y. That means I can put 4Y in for X in the first equation. That gives us 4Y plus Y equals 1.5. And that means that 5Y equals 1.5. And if I divide both sides by 5, I get Y is equal to 0.3. If Y equals 0.3, X is equal to 4 times 0.3, which is 1.2. So we have our solution. Now in this problem, it doesn't make as much sense to write the solution as an ordered pair, because what does that even mean, right? So what we know is that the domestic tourists, which is the X variable, brought in $1.2 trillion. And the foreign tourists, which is the Y variable, brought in $0.3 trillion. And you could leave your answer like this. This is fine. But I should note that 0.3 trillion is the same as 300 billion. Right? That's just a small note there. One note that I want to make before continuing is that in the beginning of the section, we talked about the different types of solutions to systems of linear equations. And I used a graph to talk about those 3 situations. So we have the situation where they have one solution, we have the situation where they have no solution, and we have the situation where they have infinitely many solutions. And the thing I wanted to point out is, although the graph is great for helping you understand the situation, notice that we did not solve any of these problems by graphing. That's because graphing is a very inexact method of solving, right? If your graph is not absolutely perfect, you may be led to believe that you have a solution which is actually incorrect. So in none of the problems that we just did we bother doing a graph, because graphing is a very messy and imprecise method. Now let's talk about a linear inequality. So an inequality in the variables x and y is a linear inequality if it can be written in the form ax plus by is less than or equal to c, or you could say strictly less than c, or you could also say greater than or equal to c or greater than c. The point is you have a linear equation, right? But instead of the equal sign, you have a less than or a greater than type of symbol. Let's take a look at a couple of examples. Suppose we want to graph the linear inequality x is greater than or equal to 3. And you got to remember, we're talking about in two variables here. So if you think about a graph, what we're looking for here are all the points in this two-dimensional system where the x-coordinate is greater than or equal to 3. Well, we can see that x equals 3 is right here. And we know that on the number line, if x is greater than or equal to 3, it's going to be all the points to the right of 3. But in the two-variable system, we have a lot more points, right? We have all these points as well. So what we do to graph this is you think of what would x equals 3 look like. And we know that x equals 3 would just be a vertical line at 3. So then x is greater than or equal to 3 is going to be all the points on either the left side of the line or the right side of the line that satisfies this inequality. Well, again, if x is greater than or equal to 3, we would have to be talking about all the points to the right of this line. So when you're graphing a linear inequality in two variables, what you're doing is you're graphing the line like you normally would, and then you're shading either one side of the line or the other side of the line to represent the solutions. In the second one, we have y is less than 2x. So to graph these points, first let's think about what does the line y equals 2x look like. So a little review here. Think of y equals 2x plus 0. 2 is the slope of the line, and 0 is the y-intercept of the line. So it passes through y equals 0 and has a slope of 2, which means we go up 2 over 1. And I could do that as many times as I want. And the line is the line that goes through these points. Now, we're going to shade on one side of the line or the other, but let me think about one other thing. We're graphing y is strictly less than 2x. So that means that the line itself is actually not included as part of the solution because it's strictly less than. So when you have a strictly less than or a strictly greater than symbol, when you graph the line, it has to be a dotted line to represent the fact that the line itself is not part of the solution. Now the only question is, which side do we shade on? Do we shade above the line or do we shade below the line? Well, if it's solved for y, it's very easy to determine which way we shade. So if you have y is less than mx plus b, right, you're going to shade below the line. And if you have y is greater than mx plus b, you're going to shade above the line. Now, why is this? It's very simple. The y variable gets larger when you go up and gets smaller when you go down. So if we want y to be less than 2x, we want the y values to be less than the line. That means below the line. So the shading occurs down here. Now, when graphing a solution to a system of linear inequalities, what we need to do is graph the solution to each one of these, and then we're looking for the points that they have in common. So first, let's graph the line. The first line we have is x plus 3y is equal to 6. And I want you to notice that both of these lines are going to be solid lines, right? Not dotted, because each of these lines has an equal to symbol, which means the line is included as part of the solution. So how do I graph this line? Well, we have a bunch of different methods, right? We could use slope and intercept. We could solve for y, or we could just plug in a couple of points. So I want you to notice that if x is equal to 0, y is going to be 2, right? So that gives us the point 0, 2. And if y is equal to 0, that's going to give us x is equal to 6, which is the point 6, 0. So we have the point 0, 2 and 6, 0, and the line goes through those 2 points. The second line is negative x plus y is equal to negative 2. And I can graph this the same way. If I let x equals 0, we get y equals negative 2, which gives us the point 0, negative 2. And if I let y equals 0, we get x equals 2. You can check my math on that, but that's the point 2, 0. And so the second line goes through the point 0, negative 2, and 2, 0. And it also is a solid line. Now I need to shade the region that satisfies both of these. To get that region, I'm going to take each equation and solve for y. So I have x plus 3y is less than or equal to 6. Solving for y, I'm going to subtract x from both sides, which gives us this. And then I'm going to divide by 3, which gives us this. In the second equation, we have negative x plus y is greater than or equal to negative 2. Solving for y here involves simply adding x to both sides. So here's the first equation, here's the second equation. Now, in the first equation, this equation here, we have y is less than or equal to this. Now, that first equation was this line right here. So what we need to do is shade below that line. And for the second equation, we have y is greater than or equal to x minus 2. That's this line right here. We're going to shade above that line. Now, which region is below the blue line? So we have to be below here, but also at the same time is above the green line. And you can see that the only region that satisfies both of those requirements is this region in between the two lines here, right? So you're not going to shade up here because these points are not below the blue line. And you're not going to shade down here because these points are not above the green line. And you're definitely not going to shade over here because these points don't satisfy either one. So when graphing systems of linear inequalities, basically you're just graphing the lines and then figuring out which region satisfies both inequalities.